All right, so now we're ready to understand what it means to be, for a system, a chemical reacting system, to be at equilibrium. So we've arrived at the conclusion that what defines the equilibrium must be that if we're at constant temperature and pressure, for example, then the free energy as we move the reaction forward or backward, as we change the extent of reaction, that can't change the free energy. If it were uh, lowering the free energy in any direction, then the reaction would continue to proceed spontaneously. But if we're at a minimum in the free energy, where the free energy is not changing as we move the reaction forward or backward, then that's when we're at equilibrium. We could write the same expression in terms of the Helmholtz free energy, but then we'd be talking about a reaction at constant T and V. And just like we've seen before, for the first time through understanding equilibrium properties, it's going to be a little bit easier to talk in terms of the Helmholtz free energy than the Gibbs free energy, despite the fact that we're more familiar with Gibbs free energy in an experimental situation. So if we're at constant temperature and volume, then the Helmholtz free energy is not changing as we move the reaction slightly forward or backward, and that's our condition for equilibrium. So let's see if we can understand what that means. If we remember the fundamental expression for that differential Helmholtz free energy, minus S dt minus PdV plus the sum of mu dn, the chemical potentials, times change in number of moles. If we're at constant T and V, then the dt and the dV terms both drop out, and we see that the differential change in the Helmholtz energy is just sum of these chemical potentials times dn. To understand what that means for a specific chemical reaction, let's stick with our H2 and Br2 example. If I have hydrogen and bromine reacting to form HBr, what this expression says, sum of the chemical potentials times the change in number of moles. If I just write those down for each of the species in the reaction, that just means chemical potential of H2 times dN, the change in number of moles of H2, plus chemical potential of Br2, change in moles of Br2, and chemical potential of HBr times change in moles of HBr. We also have learned with the introduction of this notation for extent of reaction that the change in moles of any species is some stoichiometric coefficient multiplied by the change in the extent of reaction. And remember that our stoichiometric coefficient is negative for reactants and positive for products. So the change in any amount of moles of H2, if I've reacted some amount squiggle, is just negative that change in squiggle, because H2 is a reactant and I'm losing 1 mole of H2 every time the reaction proceeds once. Likewise, I lose 1 mole of Br2 when the reaction proceeds once, so the change in moles of Br2 is negative d-squiggle. And because the stoichiometric coefficient in front of HBr is a 2, the change in number of moles of HBr is plus 2 times that change in the extent of reaction. So I can take each of these terms, dn H2, dn Br2, dn HBr, insert them into the expression we have for the change in Helmholtz free energy, and we find that dA is minus mu H2 d squiggle, so where the negative sign came because H2 is a reactant, minus Br2 d squiggle, plus 2 mu HBr d squiggle. So again, each of these terms has a stoichiometric coefficient, either a -1, or a +2, depending on whether it's a reactant or a product and what the stoichiometric coefficient is. Now that I've written these changes in number of moles in terms of the extent of reaction, each of the terms has a d-squiggle in it, so I can factor out those d-squiggles. And I see that the differential change in the Helmholtz energy is minus mu H2 minus mu Br2 plus 2 mu HBr, all times d-squiggle. Remember my goal, if I scroll backwards, upwards a little bit, the equilibrium condition is dA d-squiggle must be equal to 0 when I'm at equilibrium. So if I take this result that we've just found, which writes dA in terms of d-squiggle, then the derivative dA over d-squiggle must be 0 if I'm at constant temperature and volume and I'm at equilibrium. So that derivative is just this term in parentheses after I've divided away the d-squiggle, and that's minus mu H2 minus mu Br2 plus 2 mu HBr. Those things must sum to 0. If I move the negative terms over to the left-hand side of the equation, we get this result. The chemical potential of H2 and the chemical potential of Br2 have to add up to twice the chemical potential of HBr. So this is another condition for equilibrium. One condition for being at equilibrium is the free energy must not change as I move the reaction slightly forward or backward. Another condition for that equilibrium is that the chemical potential of the reactants, H2 and Br2, is exactly the same as the chemical potential of the products, which is 2 moles of HBr. If I move the reaction slightly forward, converting one H2 and one Br2 into 2 HBrs, the chemical potential of the whole system hasn't changed. Likewise, if I move it backwards, converting 2 HBrs into one Br2 and one H2, there's no change in the chemical potential. So in this case, we found this specific result for the H2 and Br2 reaction. In general, if I go back to this expression with the negative signs in it, the chemical potentials are going to add up to 0 if I include them with the stoichiometric coefficients out in front. -1 for H2 and Br2, +2 for HBr. So the general situation is if I sum up stoichiometric coefficients multiplied by the chemical potentials for each of the different species in my reaction, those things are going to add up to 0 if I'm at equilibrium. So if I put a box around this equation, this is an important result. This is our equilibrium condition. When we're at equilibrium, this statement holds, and what it tells us is a relationship between the chemical potentials of the reactants and the products at equilibrium. And again, essentially all it means is the chemical potential of the reactants have to add up to the same value as the chemical potential of the products. And then what we'll be able to do is use this expression plus what we know about chemical potential to learn something about how much of each reactant and product will be present when we're at equilibrium.